Welcome to another explainer. Today, we're exploring how a massive breakthrough in pure combinatorics, specifically the BSCZ bounds, structurally solves some of the absolute deepest anomalies in the Adelic Langlands program. I mean, if you've ever wondered how discrete numbers actually govern infinite continuous symmetries, you are absolutely going to want to see this.
Okay, let's dive into this. Our central mathematical mystery starts with a pretty simple premise. The classical sum product conjecture essentially assumes that addition and multiplication are fundamentally at odds. If one stays contained, the other just has to expand. But what happens when you force them into submaximal harmony? As we'll see today, these new combinatorial bounds don't just disprove an old conjecture, they completely transform how local Gauss extensions behave at their deepest levels.
Section 1. The Scale Elevator Alignment. Combinatorial Constraints at F1.
To really understand this, we actually have to shift our focus to the absolute baseline, which is the boundary of the field with one element. This structural synthesis we're looking at represents the unified topology of Logos field theory. What's amazing here is how it takes these incredibly complex, totally disparate symmetries across number theory and geometry and just unifies them. It shows us that right at this baseline, addition and multiplication dissolve into a singular regularized calculus. It's a real game changer.
So, to see how that actually works mathematically, we apply the BSZ constraint, which is known as submaximal compression. For any arithmetic set A, the maximum size of either its sum set or its product set is strictly bounded by the size of A raised to the power of 2 minus a compression factor, C. That C is super important. It represents the exact limit on how much spatial volume the set can occupy, and it's the single inequality that disproves the Erdős-Szemerédi conjecture, because instead of expanding maximally like wildfire, these variables are forced into a shared, tightly bounded space.
Now, applying this compression creates what we call scale elevators. Look at the towers of field extensions mapped out here. The local Gauss extension degree, our D variable, doesn't just grow wildly out of control anymore. It actually scales dynamically in direct proportion to the logarithm of the set size A. So this scaling essentially acts as a perfect geometric regulator.
Section 2. Bounding the parabolic horizon, the logarithmic governor.
Let's look at how this dynamic scaling completely reshapes the Hecke algebra filtration depth. Normally, deepening ramification means increasing the congruence level over a fixed field, which, creates a chaotic, infinite filtration depth. But under BSCZ limits, dynamic degree expansion bounds that capacity. Because the field degree is scaling dynamically with our data density, it establishes rigid order where there literally used to be infinite chaos.
And the math driving this whole thing is the hero equation right in front of us. Notice how the filtration depth is now strictly less than the exponential of a constant times n squared log a. So those infinite depth towers, they're structurally transformed into finite rigid capacities. The chaos is totally bounded by a strict logarithmic governor.
Section 3. Stabilizing the Whittaker model, the spectral cage.
Okay, this is where it gets really cool. These combinatorial boundaries literally wrap around the local Whittaker integrals to stabilize the model. Looking at this spectral cage, the multivariable Satake parameter string is no longer subject to chaotic continuous drift. Instead, uniform logarithmic bounds freeze these parameters into the strict discrete lattices you see plotted here. That completely prevents destructive phase shattering and ensures our local coefficients remain totally stable and non-zero.
Section 4. Exact integer trace reductions, modulo annihilation.
To see how this stabilization actually reduces down to exact integers, we really need to grasp the parabolic matrix operator. Basically, this operator maps the internal arithmetic crosstalk quadrants across root spaces right before we apply the Jacquet module functor's parabolic restriction. In plain English, it tracks the messy matrix of interactions that we need to filter out.
So the crucial point is this. Because our set A satisfies the Monach-Minkowski quadratic constraint, that's the magnitude of A plus A being less than or equal to the magnitude of A to the power of 2 minus C, the uniportant crosstalk, that off-diagonal noise, cannot escape its submaximal envelope. It strictly restricts the simple root operators, which means those messy, non-commutative matrix blocks are instantly quenched.
Now, if we track a top cell coordinate transition in GL3, our simple roots x and y, along with top cell entry z, pass directly through that Minkowski bound box. And because of that bound, the complex phase space physically flattens out. It outputs the pristine right-Haro equation you see here, locking the local epsilon factor into a rigid submaximal floor factor and clamping the conductor down, which completely eliminates wild oscillations.
And this flattening triggers the modulo annihilation of the upper triangular quadrants.
As the Jacquet functor slices the matrix, our bounds force to crosstalk terms, theta 1, 2, theta 2, 3, and theta 1, 3, to absolute zero. The output is a completely diagonalized torus frame. And when we trace this normalized space, all fractional index expansions collapse perfectly. They collapse to exactly n, an exact integer trace. No fractions, just pristine integers.
Section 5. The combinatorial exceptional zero, the arithmetic collapse. Let's move to and see how this builds up to the true climax of our analysis, step by step. First, the BSS set condition bounds our sets. Second, this extreme clustering forces a discrete rigid Satake parameter, alpha A, to equal exactly 1. Third, plugging this into the p-adic system at the critical weight causes the entire Euler multiplier to just vanish to 0. And this sequence yields a distinctly novel classification that mathematicians have been hunting for, the combinatorial exceptional zero.
Now, unlike traditional geometric topology, this zero is a structural obstruction driven entirely by algebraic packing limits. The equation highlights how the continuous fields are literally forced into balance simply because the underlying arithmetic units physically cannot expand any further.
And that ultimately confirms our final geometric consequence. The Adelic Langlands program achieves absolute, invariant geometric equilibrium. The continuous global fields of Logos field theory are held in perfect harmony by the rigid, unexpanding laws of arithmetic combinatorics. The infinite is successfully, definitively governed by the finite.
Which leaves us with this final thought for today. If pure combinatorial bounds can freeze infinite geometric chaos in the Adelic Langlands program, what other deep topological mysteries might be solved simply by counting the limits of addition and multiplication? It's like a giant puzzle, and we just found a massive corner piece. Thanks for joining me on this explainer. I hope this helped you visualize the absolute boundaries of number theory.